Hello and welcome back again. Today we're going to talk about a new concept in physics, which is energy. So let's first just talk in general about what energy really is. So everyone probably already has some idea about what energy means. We talk about energy in a variety of different contexts, right? We say that moving objects have energy. Um, Energy is the ability to make things happen. If you have a lot of energy, you're able to move a lot. It's also associated with heat and with electricity. We talk about how much energy you're using in your house when you're using electricity. We're always told to, conserve energy. What does it mean to conserve energy? Why is it important? Uh, People, animals, plants all need energy to live. Why is that, and where does that come from? And of course, as engineers, you have to worry about trying to harness energy to do useful things. So we want to take energy and transform it into different forms. So energy is a really important idea in many different areas of physics and engineering. In fact, many scientists consider the law of conservation of energy, which we're going to learn later in this chapter, to be probably one of the most important, if not the most important, of all the laws of nature. So let's first talk about a few different kinds of energy. First, kinetic energy. Kinetic energy is the energy of motion. This is one of the primary ones that we're going to study this semester because the theme of all of Physics 1 is about motion. So all things that are moving have kinetic energy from small to large objects. The more massive an object is or the faster it moves, the larger its kinetic energy. And in just a little bit, we'll learn how to actually calculate how much kinetic energy an object has. Another important type of energy that will be very important here is called potential energy. Potential energy is energy that's stored in a system because of the position of an object. One of the important kinds of potential energy is gravitational potential energy. So in this case, if you have a roller coaster that goes up to the top of a hill, it has potential energy. It has gravitational potential energy that's proportional to how high it is. And as it goes over the hill and starts going back down, that potential energy can turn back into kinetic energy and the car is going to speed up. Another important kind of energy is thermal energy. So thermal energy is energy that's within a object or a system of objects that is due to the temperature of the object. It's really a kind of kinetic and potential energy, so it's the sum of microscopic energies of all the atoms and bonds that make up the object. As an object gets hotter, it's going to have more and more and more thermal energy. Those are the three big ones that we're going to look at right now, although they are not the only kinds of energy. The next important thing that we want to talk about is something called work. Work is a way that we transfer energy into or out of a system. So energy is something that a system has. It can have different kinds of energy, but it's a thing. It's an amount of a quantity that a system can possess, and it can gain and lose energy. And how does it gain and lose energy? Well, there are several processes that can happen to make it gain or lose energy. The two main ones that we're going to look at are called heat, and they're going to be and work. Heat is any process that transfers energy using thermal means, and work is a process that transfers energy using mechanical means. So we're mainly right now going to look at the mechanical side of it because we're studying motion and mechanics. How is energy transferred via work? So here are a few examples of how energy is transferred into or out of a system. So in this case, you pull back a slingshot, right? The buoy, which is considered part of the environment here, if the slingshot is the system, then the buoy does work on the slingshot by stretching it, right? So he exerts a force on the slingshot, pulls it back. By doing that, he is putting a little bit of his energy into the slingshot. He has to use some energy to pull back the slingshot. And then when he lets it go, that energy can then be eventually turned into kinetic energy. But right now in this picture, it's potential energy. It's what we call spring or elastic potential energy because it's stored in the stretching bonds in the slingshot. So he transfers some of his energy to the slingshot. It's stored in the slingshot. Then if he lets go, that's going to come out as kinetic energy. Another example. In this case, if we make our system the diver and the earth, then we have energy that's being transferred from potential energy into kinetic energy. So the diver is speeding up as his gravitational potential energy is transformed into kinetic energy. Finally, let's look at it on a bigger scale, a speeding meteor. So in this case, of our system is the meteor in the air, then as the meteor goes through the atmosphere of the Earth through the air, then its kinetic energy is turned into thermal energy because of friction with the air, drag forces with the air as it moves through the air. And that slows it down. And where does that energy go? Well, it turns into thermal energy, heating up the meteor and the air around it. It's usually hot enough for it to glow, and that's what we see in the sky as a shooting star. So energy can move in or out of a system. It can also change forms within a system. It can go from potential to kinetic and back in many different ways. But as long as the total energy inside the system stays constant, then we're not really transferring energy in or out of the system. That doesn't require any work as long as the total energy stays the same. But if the total energy in the system increases or decreases, then that requires something to make that happen. And one of the ways, as we said earlier, that can happen is by means of work. And right now, we're only going to consider work as the only way to transfer energy, although it's not the only way. There are other ways to transfer energy. We're just not going to be looking at those right now. We're just going to look at how does work transfer energy. So we can write a very simple equation, which says that the amount of work done by external forces, that's what the EXT means, is equal to the change in energy of our system. And that makes sense, right? So if you do positive work on the system, you increase the energy of the system. If you do negative work, that means the system is doing work on the environment then, and so energy is leaving the system. So summarizing what we have learned so far, all these ideas make up what we call the basic energy model. So energy is a property of a system. It's a quantity that it possesses. And importantly here also, energy is not a vector. So that makes it different from something like forces that we talked about in earlier chapters. Energy can be transformed within the system into different forms without losing any energy. So it can go from kinetic to potential to thermal and back again. But if energy is transferred into and out of the system, that can happen by means of heat, work, and a few other things. But for now, we're just going to consider work because work is the way that we transfer energy using forces by mechanical means. So if energy is added to the system, the work is positive, right? Work is greater than zero. If energy is removed, then the work is going to be less than zero. Now let's look a little bit more detail at the different types of energy that we can have. Let's look at kinetic energy in particular, and how does work affect that. So consider you have just one particle that's acted on by a constant force, just one force. We're going to start with a very simple model, and it acts parallel to the direction of motion, pushing or pulling the particle as it undergoes a displacement, which we'll call delta S. We're going to define the particle as the system, while the force is going to be in the environment. So we know right away that that force is doing some work on the particle because it's coming from the outside and it's acting on the particle, so it's transferring some energy to it. All right. So initially, we have the particle right here. We have the force pushing on it and it has one speed. After a while, the force continues to push through this displacement. What do you notice about the speed here? It's bigger, right? And that's what we'd expect. If you continuously push on an object with the same force, then you're going to give it an acceleration. That Newton's second law tells us that, which means that it's going to speed up. So it's going to have a higher speed in the end. We can also think about that in terms of energy. If you apply a force to it, you are doing work on the system, the particle here, therefore increasing its kinetic energy in this case. How do we calculate kinetic energy? Kinetic energy is determined by the mass of an object and also its velocity. So if either or both of those goes up, then the kinetic energy also goes up. So kinetic energy is formally defined as equal to 1/2 mv squared, where m is the mass and v is the speed. The unit of kinetic energy is called joules. In fact, this is the unit for all forms of energy. So we're going to use joules a lot. A joule is equal to 1 kilogram times meter squared per second squared. Okay, so now let's look at how kinetic energy is related to work and see if we can figure out how to calculate how much work is done. Well, remember the energy principle. The energy principle said that the change of energy in a system is equal to the work done from the outside. In this case, the only kind of energy we've talked about so far is kinetic energy. So if the work done just changes the particle's kinetic energy, then we can set those equal to each other. Now, how do we calculate work? Well, it depends on the orientation of the displacement and the force and how those things work together. In general, we can calculate work by saying that work is the integral from the beginning point to the ending point of the force times the displacement. Right? That's what ds represents. Now, if we're talking about something going in a straight line with a force that's parallel to the direction of motion, then work is simply equal to the applied force times the distance over which that force acts. So it's force times distance. Because work is a way to transfer energy, it has the same units as other kinds of energy, which are just joules. Now, even when you just have work that's acting in a straight line, it's not always the same. Work can either be positive or it can be negative, depending on which way the forces are applied and which way the object is moving. So, in general, work is positive when the force acts in the same direction as the displacement, and work will be negative when the displacement and the force are in opposite directions. And when you have positive work, then that force causes the particle to speed up. It increases the total energy, making it go faster. When you have negative work, then you're taking energy out of the system, therefore you're making it slow down, losing energy. You can also have zero. Work can be zero. Even if you apply force to something, if it doesn't move at all, then you have no work being done. So I could stand and push on the wall all day long, and if I don't push the wall down, then I'm not doing any work on it, no matter how hard I push. All right, let's look at a quick question then related to the previous topic. In this case, you have a crane that lowers a girder into place at a constant speed. Let's consider the work done by gravity and the work done by the tension in the cable. Which of the following is true? Well, remember we said, how do we know if work is positive? Work is positive if the force applied and the displacement are in the same direction. In which case is the force that's applied and the displacement in the same direction? Well, which way is it moving? It says that it lowers the girder into place, so we can assume from that that it's moving down. Which force is going to be acting down? If we think about, we can draw a quick sketch over here. If we have the girder, right, the weight will be acting down, and the tension force, the T there for tension force, the tension force will be acting up. So if it's moving down, its displacement is down, then the force of gravity and the displacement are in the same direction, which means that the work done by gravity will be greater than zero. What about the tension force? Well, the tension force pulls up, and the displacement is down, so the work done by the tension force will be less than zero. And what if we ask what's the total work done? Well, the total work done in this case would be zero. How do we know? Because constant speed. If it's not speeding up or slowing down, then the total amount of kinetic energy in the system is not changing. So the total would be zero. Another related question. In this case, we have Robert who's pushing a box to the left at a constant speed. In doing so, is he doing positive, negative, or zero work on the box? Well, he's pushing it to the left, right? So he's exerting a force this way. And it's also moving to the left. So that would be positive work. Now, it's going at constant speed, once again, so how is it possible that it's having positive work done on it and it's not speeding up? Well, again, Robert's force is not the only force that acts on it. What other force do you think acts on the box? There's a friction force with the ground. Which way does the friction force act with the ground? It's going to act opposite to the direction that it's moving. So, this way. Friction force is going to be doing negative work. So once again, the total work being done on the box would be zero. Now let's look at what happens if the force is not applied in a straight line. So if you have a constant force, once again, but it's not in the same direction as the displacement, how do we find the work done in that case? Well, in that case, what we want to do is we want to take just the part of the force that is in the same direction as the displacement. And how do we find that? Well, we use cosine, just like we have for other kinds of vectors. We want to find just the component of the force that's in the x direction. So in that case, the work done would be equal to the force times the displacement times cosine of the angle between them. All right, let's look at another question related to that. Which of the forces shown below will do the most work? So we can assume that all three displacements are the same. So the one that does the most work will be the one that has the biggest component of the force in the same direction as the motion. Well, here, let's look at the first one. How much work does the 10 Newton force do? If you notice, they're at a right angle to each other. So is there any component of that force that is in the direction of the displacement? No. So this one, in fact, does no work. Now, what about the second one? The second one does some work. How much work does it do? Well, it would be equal to the force times the displacement times cosine of the angle between them. Cosine of 60 would be 0.5. So the amount of the force that's in the direction of motion would only be 4 newtons, compared to the last one where all 6 newtons are in the direction of the displacement. So the work in that case would be the biggest. Now finally, let's look at an example problem. Here we have a strap inclined upward at a 45-degree angle that pulls the suitcase for 100 meters through an airport. We know that the tension in the strap is 20 newtons. We want to figure out how much work does the tension force do on the suitcase. So let's let the system consist of only the suitcase. So to start with, we still want to start by thinking about making a free body diagram here and figuring out what forces we have acting on this situation. So here we were going to have 4 forces. We're going to have the weight of the suitcase. We're going to have the normal force. We're going to have some kind of friction force as you pull it across the ground. And we're going to have a tension force, which we're told is 20 newtons. And we're also told is exerted at a 45-degree angle. So now how much work is done specifically by the tension force? We don't have to worry about the other forces just for this problem. The work that will be done, because it's at an angle, the work will be equal to the force applied times the displacement times cosine of the angle between them. The force is 20 newtons. The displacement is 100 meters. And the angle between them is 45 degrees. So this means that the total work done will be 1,414 joules. Let's look at another question. Once again, we'll start with a free body diagram. This one's a little simpler because we only have 2 forces. So we have the thrust force acting up, which we are told is 4 times 10 to the 6 newtons. And we have the weight acting down, which will be m times g, which we can calculate is 1.47 times 10 to the 6 newtons. Now the question says, how fast will be the rocket's speed at a height of 500 meters? So we can figure that out using work and energy. We could also do that using Newton's laws, but right now we're going to try to do it using work and energy. So work and energy, or energy theorem says that the amount of work done equals the change in energy. In this case, we're just going to look at kinetic energy. We haven't added in any other kinds of energy just yet. So we need to figure out how to determine how much work is done, and then we can figure out what the change in kinetic energy is. And then we can use that to find the speed, because kinetic energy is equal to 1/2 mv squared. So how much work is done here? Well, which way is it moving? It's moving up in the y direction, a distance of 500 meters. So we can figure out the work done by each of these forces. The work done by the thrust force will then be the force times the displacement. And since the force and the displacement are in the same direction, in this case, this is positive work. Total of 2 times 10 to the 9th joules. How much work is done by gravity then? Well, this will be negative work, first of all, because the force of gravity is acting down and the displacement is directed upward. The total amount of work done by the force of gravity is negative 7.35 times 10 to the 8th joules. Now let's look at the kinetic energy side. The change in kinetic energy. Well, what was the initial kinetic energy? It's launched from the ground, it started at rest, so the initial was 0. The final would be equal to 1/2 m times final velocity squared. So on the work side, we can have the total work done by both of these has to equal the final kinetic energy minus 0. Then we can put in what we've already found. Here, the work done by the tension force was 2 times 10 to the 9th joules. The work done by gravity was negative 7.35 times 10 to the 8th joules. The mass is 150,000 kilograms times VF squared. Solving that for VF gives a final velocity of 130 meters per second.